and we're going to be hearing about neural network parameterization of subgrid momentum transport learned from a high-resolution simulation. So, Janni, I can see your slides. So when you're ready, please take it away.
Thank you. I just said I did this work with Paula Gorman and Peidong Wang. Just to give some context, what we are doing is that we want to use machine learning to create new parameterizations trained on a high-resolution model. So the idea is that we have this great asset nowadays of high-resolution models that we consider them more accurate, as they don't need to use as many parameterizations as a coarse resolution model. However, they are expensive to run. We can only run them for a limited amount of time on a small domain. And the idea of machine learning parameterization is to somehow use this high-resolution model to develop new representations of subgrid physics, such clouds, convection, turbulence, and so on, and implement it back into an atmospheric, into climate model or atmospheric model, and still rely on the laws of physics where we can. So building this kind of a hybrid model. And this approach of building such hybrid models has been getting a lot of attention, and there has been some success and some nice insights. However, there are still kind of reoccurring features that we saw also in last talks, that we have sometimes unstable simulations, meaning like literally numerical instabilities when we are having this hybrid system. And sometimes we get a climate drift, so we cannot obtain statistics over the long run. And I should mention again that this kind of machine learning algorithms do not obey physical constraints, at least not by default. And our hope is still somehow that this kind of a hybrid system, the dream is that it will really create a more accurate climate and maybe weather models and so on. And in a previous study, what we've done, we've achieved a physically consistent parameterization. We were able to somehow represent the physics in a way that we conserve energy, we conserve mass, and that lead to stable simulations and accurate simulations. So what do I mean? In that, here I'm just showing snapshot. The left one is a latitude, longitude. What we use, the colors show precipitable water, so just the amount of water in each atmospheric column. And these are snapshots from high resolution and coarse resolution simulations in the middle. So you can see that there are large differences in the large scale organization of the atmosphere. Here we have a single like red peak, single rain band ITCZ. However, in a high resolution, you get a very different picture of a double ITCZ. When we run a coarse resolution model with a machine learning parameterization, we're able to capture this double ITCZ, and we show that we get the correct statistics of precipitation, wind, and so on. So we overall kind of had some success of using coarse resolution model with a machine learning parameterization that allows us to get statistics which is fairly close to a high resolution model. And in this talk, I'm going to focus on something slightly different. So far, most of the applications of using high resolution models were concentrated on somehow parameterizing the effect of subgrid processes that affect moisture and thermodynamic variables, so convection, clouds, radiation, and so on. But here, if we really want to have a fully climate model and correct it, we somehow need to also correct momentum transport. And the reason that we want also to correct the models for subgrid momentum transport is because convective momentum transport really affects the circulation. So just to name one thing that it's really important, it can really affect surface winds, and surface winds are interacting with ocean and determine evaporation. So overall, convective momentum transport can really affect tropospheric circulation. And not only convective momentum transport can have a large effect on the circulation, we also have gravity waves. So this kind of, here you see them as nice patches in these clouds. So gravity waves have large impact on the stratosphere, on the QBO, and so on. So these kind of two processes that are overall subgrid in current climate models, and we need to somehow represent this subgrid momentum transport due to these processes. So I want to first focus on how we produce, even how we use this high resolution model to produce the outputs we really want to predict, the subgrid momentum outputs, and how we do it in a physically consistent manner. So here I'm showing a snapshot of the surface zonal wind. So it's a latitude versus longitude map of a high resolution run. I'm taking an inset, I'm zooming in into kind of 100 by 100 kilometer domain, which kind of represents our climate model domain. And you can see that in this kind of domain, we have here some positive wind, some negative wind. However, if we would have run a climate model at 100 kilometer resolution, what we would see, we won't see this kind of a rich structure. What we would see kind of average zero wind or maybe slightly negative wind. And this already raises a concern. Okay, we have here some subgrid fluxes that we need to take care of. And I'll try to explain how now we define these subgrid fluxes that we are going to try to model. And so ideally, we would like to run our course model with this quantity. So what is written here, we are trying to model vertical advection now. So subgrid vertical advection. So the flux is just the vertical wind W, the high resolution vertical wind, times the high resolution zonal wind coarse grained. This bar is just coarse grained, average over this 100 by 100 kilometer domain. However, what we are really able to run our models with is what we really resolve when we run these models, which is the coarse-grained vertical wind times the time to coarse-grained zonal wind. And the difference between these two is what we are calling subgrid flux. And I'm insisting of calling it flux, but because when we are modeling fluxes and not tendencies, for example, we are guaranteeing that we conserve momentum because we don't add momentum to any grid box. We just move momentum from one grid box to another. And I should mention that how we do it, we look at a single atmospheric column. This is a very typical approach in atmospheric dynamics. So our parameterization will be at first single column. We take the inputs from this single column, temperature, moisture, winds, and try to model the subgrid advection, vertical advection in this atmospheric column. Towards the end of the talk, I'm going to revisit this decision of looking at only a single atmospheric column. So now let's see how our machine learning can learn these kind of tendencies. So here I'm just plotting some offline results. So on the left, these are true zonal momentum subgrid fluxes. So in the tropics, we have an upward fluxes. In the extratropics, we have downward fluxes. And the machine learning can kind of emulate it almost perfectly over at least the mean. And the reason that it's just like a side comment that there is an upward flux in the tropics and downward flux in the extratropics is because of the shear. So basically we have the contours represent wind shear. So we have basically down gradient or transport at least over the mean. And now really let's look just still on offline results. How well are we able to determine this kind of instantaneous fluxes? So these are the results for zonal mean fluxes. It's pressure versus latitude. Colors indicate the coefficient of determination. So one is perfect result. And the offline results are kind of poor. So let's give a reference. We can repeat the same exercise and ask how accurate we can predict moisture fluxes. And moisture fluxes, we have much better ability to predict. Basically, brighter color means we are doing a better job. And now the question we want to ask, okay, why is it so difficult to predict momentum fluxes? Why are we failing in predicting momentum fluxes? So to do that, I'm looking at a single grid point at some time interval. So in the upper plot, I'm plotting precipitation versus time. And you can see what happens here. This is a tropical region. Every once in a while, we have a lot of precipitation, and then maybe nothing, and again, precipitating events, and so on. Below it, I'm plotting the subgrid moisture fluxes. So every time we have a precipitation event, you can see we have an upward moisture flux. And this is a convection event. So this makes sense. Moisture is brought from the surface upwards for every time we have a convection event. But below it, I'm plotting the true subgrid momentum fluxes. And I just want to focus on this kind of two precipitating events. So you can see that momentum fluxes can be both positive or negative. However, when we have convection, moisture and energy always obtain the same sign. For example, for moisture, we always bring moisture upwards in a convection event. But for momentum, the task is different. And what we discover, it's very difficult to get the sign correctly for the momentum transport in this kind of a single column parameterization. And we can get the amplitude of the transport very accurately, however, not the sign. And it's not new that convective momentum transport can be both positive or negative. And there are some ideas, and the idea is that basically the way the cloud tilts during convection will determine basically the sign of momentum transport. The second reason that we find that it's very difficult to get momentum transport correctly is because of gravity waves. So at least linear gravity waves do transport momentum, but they don't transport conserved thermodynamic variables. So this is like an explanation why it would be more difficult to predict momentum fluxes compared to moisture or energy fluxes. And So still we want to try our parameterization in an online setting. Like everybody said, offline is nice, but what we really want to test it is in an online setting. So to do that, I'm plotting here the surface meridional wind. I'm focusing on meridional wind since convective momentum transport is very crucial for surface wind. And I'm just showing here amplitude basically versus latitude. So the first line just shows the high resolution. So this is our target. This is what we want to be at. And the green line shows a low resolution simulation with no machine learning parameterization. So you see that there are big differences both in tropics and extratropics. And the third line, the blue line, is a simulation at low resolution where we implemented the neural network parameterization for moisture and thermodynamic variables, but no momentum. So still it does somewhat better. I would say the blue line is closer to the black line than the green line. So it fixes something, but there are still large gaps, both in extratropics where we didn't fix anything, and still in the tropics, there are large gaps. The last line, which is a simulation, we ran a low resolution simulation with a neural network for all variables, so including moisture, thermodynamic, and momentum variables. And the simulation is stable, we can run it for a long time. And you can see already that the red line is much closer to the black line compared to the other simulations. So basically we have an online simulation when we implemented the neural network parameterization for momentum, and it fixes or corrects some aspects of the circulation to be closer to the high resolution simulation with the caveat that we know that it was very difficult to predict these momentum fluxes. So now we want to go basically to revisit this decision of using a single column parameterization. So basically I think the kind of in the atmosphere there, what people think about atmospheric parameterization is the following. We look at an atmospheric column. We need to model like processes that transport things in the vertical, like convection, clouds, and so on. And we use information from this vertical column, temperature, moisture, wind, to model these processes. However, we know that we have, let's say, mesoscale convective systems that have like large area that it can reach 100,000 square kilometers. And if we just like put them on our caricature of a climate model here, these kind of systems are larger than any grid cell of the model. So you might think that maybe if we would use information not only from a single column, but use also information from the vicinity, let's say in this case, 3 by 3 columns, just information to predict what happens in the center column would be useful. So this is basically what we try to test here. We try to use a different parameterization, which is a non-local parameterization. So let's see how it performs. So in the y-axis, you can see the performance, like r squared, and the x-axis is the latitude. The blue line represents the performance of the single column parameterization, and the orange line shows the performance of a non-local parameterization. And you can see that the orange line is above the blue line, meaning this non-local parameterization really improves the prediction of subgrid momentum transport. And the next question I want to ask is why? I mean, it's nice that we have developed something that slightly or substantially improves the prediction of subgrid momentum transport, but we really want to understand why. And to do that here, we try to look on, so in the upper panel, in these 10 snapshots, you see samples, inputs to the neural network, colors indicating cloud mass per unit area. So basically white colors are the clouds. And we look at samples that were really improved. We could really improve the prediction of subgrid momentum transport when we use this non-local parameterization. So each box here is like one coarse grid box, and the clouds are taken from the high resolution model. And below it, these 10 samples, you can see samples that we took from samples that we took from our set that we did not improve the prediction by using non-local information. And you can see already there are some kind of differences. In cases we really improve the prediction, the shape of clouds are slightly different. They are more concentrated. There are like sharper features here compared to cases we could not improve where clouds were more diffused and spread around. This is interesting by itself, but what we can do now is really look at samples that we really improved and try to understand where the network looked to determine the effects of convection. So the idea here is to use an explainable artificial tool. Specifically, we are using a layer-wise relevance propagation to really determine where did the network look to determine the effects of convection. So let's look how it looks like. So we have 4 input features for the parameterization. We have temperature, moisture, zonal wind, and meridional wind. Each feature is 3-dimensional. We have this latitude, longitude, the 3 by 3 boxes we give the information, and we have the vertical column, which I collapsed here. I don't show it. And let's look what we see. So bluer color means the network really relied on this information to make a better prediction. And you can see, for example, the network really relies on moisture in the center column. That's great. It makes sense. Every parameterization relies on this quantity. But what's interesting, if we look at our wind variables, we see that the network also relies on non-local features. For example, for the zonal wind, east and west, also some, of course, north and south, but you can see that it really relies on non-local features when it predicts, when it makes its prediction. And now we can go maybe to the next step and try to understand how and why it uses these features and develop and improve our both machine learning parameterization, but maybe even understanding a bit better how to build better parameterization in a conventional sense. What we need to provide the parameterization and maybe why it uses this information to improve its prediction for these cases. So I want to end with my conclusion. So basically, the first part, I talked a bit about how we can achieve this physically consistent neural network parameterization for subgrid momentum, learning from a fully three-dimensional model that we are modeling fluxes and not tendencies, which allows us to guarantee a conservation of momentum. I showed that it's pretty challenging to predict subgrid momentum fluxes, mostly because it's very difficult to determine the sign of these subgrid momentum fluxes. We can easily identify convecting events, but not necessarily identify the sign of convection of momentum transport. And we even implemented the parameterization online and shows that it improves some features of the simulation. So with this, I want to end and thank you for listening.
Thank you, Janni. That was a wonderful talk, really nicely explaining how and why you were able to have success. I encourage people, if they have questions, to answer them or to ask them in the chat, and I will relay them. In the meantime, I mean, you've been working on building these schemes for a while now, making really nice improvements over the time. Where do you see yourself going next? What's the next challenge? Because this was obviously a nice next hurdle, but what do you think would be the next thing to do?
So I think realistically, the most important thing is we should now start putting them in Earth system models and real models. And this is one thing that we're doing. We're trying to implement this kind of parameterizations currently in CAM, which is a part of CSM. This, I should say, it's fairly challenging. There are both conceptual challenges and technical challenges. So I think putting aside for a moment the momentum transport problem, if we're talking about really plugging this kind of machine learning parameterization into real models, there are problems that at least personally I haven't thought of. I just mentioned a few. For example, I think the largest problem is how to make all parameterization really interact, because radiation, for example, I don't think that we should change in Earth system models. Radiation scheme is fairly accurate, and personally, I think if we really want to train a really good neural network parameterization, we probably need a lot of data, because we need to give the inputs all gas tracers and so on that affect radiation. But I'll just give an example. In CSM, radiation expects to get certain inputs from the current suite of traditional parameterizations, like penetration depth, distribution of cloud droplet size and stuff like that, that probably, at least I never thought that I would need to predict with using machine learning parameterization. This is not how machine learning parameterization is thought. So basically, how I think some climate models are built, that there are some kind of crosstalk between current suite of parameterizations, and it's making it very, very difficult to just substitute some parts of it. So you need to somehow still think about how you're going to do it. And of course, there are issues of you need to retrain. So you plugged in, maybe you have really improved certain aspects of your convection scheme, but some other parameterizations probably have been tuned not considering this kind of changes you're doing to the model. And these are just two small, both technical and conceptual problems, but there are many of these kind of things that come up when you're really trying to code it into Earth system models. And I think it's interesting how people are going to approach these issues, I would say.
Yeah, no, I think that's a really good point, and I hope if you're able to come back later in the discussion, it's something that we can talk about as a group, because I think it's a really important thing that we're perhaps not thinking about enough at the moment. Just quickly, we'll do a few questions because we've got a long coffee break, so we can overrun slightly. So a question from Mikhail Languth regarding the estimated momentum transport. Convective momentum transport is influenced by cross-draft pressure gradients, which pushes the momentum towards the ambient momentum profile. Could this explain the results?
No, so basically this, I mean, if I understand correctly the question, this is an issue, I think, in conventional parameterization, when some momentum parameterization do include this pressure gradient. Inherently, it is included in our parameterization because we really calculate this pressure problem is in conventional parameterization is introduced to kind of recalculate the subgrid fluxes, but we calculate the subgrid fluxes accurately. I put quotation marks accurately given the data that we have from our high resolution model. So it is by inherently we are trying to predict something that already took care of this pressure gradient. I should say that there is a totally different question of a pressure gradient, which is a subgrid pressure gradient. It has nothing to do with convection. It's really the pressure term. It's nothing to do with the momentum transport, the W prime U prime term, or W prime V prime. It's just a subgrid momentum term that would affect your momentum tendency. This is a separate question, which I can discuss later during the talk, during the coffee break or discussion. But I don't think that this okay. is the reason, but maybe I missed the question.
Okay. Great. I think we have a question from Nathan, which is, do you know the model computational stencil and whether it was correlated with the neural network relevance in the horizontal scale? Was the model semi-Lagrangian, for example? It would seem reasonable that upstream are important inputs for the dynamical model.
I am not sure I fully understood the question. I'm sorry.
No, that's fine. I think perhaps it's one to, I'll send you a link in the chat to have a read and we can come up with, I think it's probably one to dwell on a bit longer. Okay. And finally, a question from Julian Lusama. Thanks for the great talk. I don't know much about parameterizations of momentum fluxes in atmospheric models. Could you confirm that these schemes generally neglect non-local brackets lateral effects? Yeah, so generally, I think as far as I know, all parameterizations in the atmosphere, current parameterization are based on this single column parameterization. So it is as far as I know that this is basically all parameterization. So including these non-local effects, it is new in the sense that I don't think any parameterization had tried really to implement it or did do it in the past. I know that I should say that in the atmosphere, we are mostly focusing on this vertical column transport, which is the major error source. And I know probably it's coming from an ocean like that, where there is also a lot of focus on horizontal transport, subgrid transport. And this is not a question we are solving here. We are focusing on this W prime, U prime terms and W prime, V prime. The vertical is the major error source in atmospheric model. So mostly I think the reason this is why this parameterization are in the first place are given as a single column with this conceptual view that this is what we need to target, this transport in the vertical that we are missing. Wonderful. Thank you very much. Well, with that, I think we will break there. We're going to take a coffee break for about 35 minutes now, so you can really have a chance to stretch your legs, everyone. And we're going to come back at 3:40 UK time. That's 4:40 European time, and I can't do the calculation for East or West Coast, I'm afraid. You'll have to do that on your own, when we will be hearing on quite a similar topic about gravity wave drags components. So please do join us back then, and thank you for watching, and thank you, Janni, for a great talk.
Thank you very much.